Welcome to the deep dive. Today we're getting into state machine diagrams. You shared some great lecture materials on this.
Yeah, looking forward to it.
So our goal today is really to unpack what these are, why they're useful, and how they show, an object's behavior over its life.
Exactly, like its life cycle.
Yeah.
You got your notes covering the basic states, transitions, all that.
And some examples too, right? Lamps, cars.
Yep. Seminar registration, alarms, course web logins.
hmm
We'll use those to make it concrete. The idea is to get those aha moments, keep it clear.
Okay, great. So let's start at the beginning then. What exactly is a state in this context?
Good question. Well, think of it as just a specific condition, a situation an object finds itself in at a particular time.
Like on or off?
Precisely. Like your notes mention a light bulb, on, and, or OFF. Or think of a fan. It could be off, low, medium, high. Those are its states.
Okay. Or a car being parked, idle, driving.
You got it. Objects can be active, idle, waiting.
Hmm.
Lots of possibilities depending on what you're modeling.
Right. So that brings us to the diagram itself. The UML state machine diagram. What's its specific job?
Its job is to model the behavior of one single object through its whole life. It shows the sequence of states it goes through based on events happening.
Just one object?
Yep. Primarily focused on a single class or object, especially one that is, well, interesting dynamic behavior. Things that change state a lot in response to stuff.
Makes sense. And visually, what are we looking for in these diagrams, the key parts?
Okay, so the main things are states themselves, which look like rounded rectangles with the state name inside, like ON or idle.
Uh-huh.
Then you have the starting point, that's a solid black circle, the initial state.
The beginning.
Right, and sometimes there's an endpoint, the final state, which looks like a circle with a dot inside, like a bullseye.
Okay. And the movement between them.
Arrows, those
Yeah.
are the transitions, showing how you get from one state to another.
Got it. Now, I saw something called a self-transition. An arrow starting and ending on the same state. What's that about?
Ah, yeah, that's a useful one.
Yeah.
It basically means an event happens, and the object, well, it kind of exits and re-enters the same state.
Like a reset within the state?
Kind of, yeah. It can trigger exit and entry actions for that state without actually moving to a different state. It's often for handling internal events or refreshing something.
Interesting. Okay, let's talk about the different kinds of states mentioned in the notes.
Right, so the most basic is just a simple state, just the name in the rounded box, idle, running, whatever.
Okay, simple enough.
Then you can have simple states with compartments. You draw a horizontal line inside the state box.
And what goes in there?
Internal behaviors. You can specify actions like entry what happens the moment you enter the state, exit what happens just as you leave, and do an ongoing activity while you're in that state.
Can you give an example of that do activity?
Sure, like in that seminar registration example, maybe the enrollment open state has a do increase seat count activity that runs every time someone signs up, but the state itself remains enrollment open.
Ah, I see. The activity happens, but it doesn't cause a state change.
Exactly. Until maybe capacity is reached, which could then trigger a transition.
Got it. And then composite states. Sounds more complex.
They are, but they're powerful.
Hmm.
A composite state is basically a state that contains other states nested inside it. It has substates.
Like zooming in?
Yeah, that's a great way to think about it. You can show these substates in a special compartment, or sometimes just use an icon to show there's hidden detail inside. It helps manage complexity.
And these substates can run one after another.
They can be sequential, yes, or even concurrent, running in parallel within the same composite state. Those are called orthogonal regions.
Okay, that handles a lot more detail. So we have states, and the arrows are transitions. What makes a transition happen? What's the trigger?
Good question. Every transition needs a trigger event. It's what causes the potential shift from the source state to the target state.
And what kinds of triggers are there?
The notes list three main types. First, a call event, like an operation being called, maybe button pressed. Second, a change event when some condition becomes true, like when temperature 100.
Makes sense.
And third, a time event simply after a certain amount of time passes, like after 5 seconds.
Right, and I think the notes mention guards and actions on transitions, too.
Absolutely. A trigger might happen, but a transition often have a guard condition like a test in square brackets, count max. That must also be true for the transition to actually fire.
So the event happens and the condition is met.
Exactly. And then optionally, there can be an action tied to the transition itself, written after a /now. This action happens during the transition, after the trigger and guard check, but before you fully arrive in the next state.
Okay, that adds a lot of precision. Let's look at those examples. The lamp.
Pretty simple. Off, on low, on medium, on high states. Transitions triggered by, presumably, button presses. You can imagine entry actions like set brightness.
And the seminar registration.
That goes proposed scheduled enrollment open. We mentioned the due activity enrollment open. An entry action there might be set seat count to 0, and exit could be save final count.
What about the burglar alarm? Resting, set, ringing.
Right, resting to set, maybe arming it. Set to ringing if triggered by a sensor. Then from ringing back to resting if turned off, or even from set back to resting if disarmed before triggering. Notice it doesn't really have a final end state.
Ah, good point. It just cycles. And CourseWeb login.
And you start not logged in, need a valid username password trigger, call event maybe, plus a GAR credentials valid to get to logged in. From there, a log off trigger takes you back.
And the timeout.
Yeah, that's a time event.
Mm-hmm.
After 5 minutes inactive, transitions you from logged in back to not logged in.
Cool. The ATM example looked quite detailed with those composite states.
It really does. It goes off self-test. If the test fails, transition to out of service. If it passes, transition to idle. Then from idle, when a card is inserted, it enters the serving customer composite state.
And inside that?
Inside serving customer, you have substates like customer authentication, selecting transaction, processing transaction. Some of those might even be composite themselves, hiding more detail.
Wow, layers within layers.
Exactly. And it shows exit actions, well, when leaving serving customer, maybe there's an exit eject card action, then it goes back to idle, unless a failure sent it to out of service.
Okay, that really shows the power. One last comparison. State charts versus activity diagrams. What's the core difference?
The main thing is scope. A state machine diagram focuses intensely on one object and all the possible states and transitions it can go through in response to events during its lifetime.
Okay, single object focus.
Right. An activity diagram often shows a workflow or process that might involve multiple objects interacting. It usually shows one specific path or scenario through that workflow, not necessarily all possible states of any single object.
So state diagrams are about the reactive life cycle of one thing, activity diagrams more about a process flow, possibly involving many things.
That's a good way to put it.
Any final tips for making good state diagrams?
Keep them simple where possible. Ask yourself if every state can be reached, and if every state, except maybe a final state, can be exited. Avoid those black hole states you can't leave or miracle states you can't enter. If it gets too messy, think about using composite states.
Great advice. So it's clear state machine diagrams are, well, a really powerful way to visualize how things change over time based on what happens to them.
Yeah, they break down potentially complex behavior into these understandable chunk states and the clear rules transitions for moving between them.
So for everyone listening, think about things you use daily. Your phone, maybe your microwave, software apps. Can you start to picture their states?
Like idle, ringing, in call for a phone. What events trigger the changes?
Exactly. This deep dive, just gets us started. There's more depth to these diagrams, naturally.
For sure. But hopefully this gives everyone a really solid foundation to build on.
Definitely. So what other system modeling topics or maybe software engineering concepts are catching your interest? Let us know and we can dive in again.